Are we ready?
Okay. Please help me welcome the Tunnel Oven Sensor Array Microcontroller Group.
Hello all, thank you for coming out this evening. Friends, family, faculty, we'd love to have you here. My name is Matt Werner. I'm the group leader for the senior project. We are the optimization of a sensor array microcontroller senior project. Our advisors are Dr. Mark Ruber and Dr. Mike Bright. We are sponsored by Dr. Michelle Hovey. So Dr. Hovey is a name you're probably not familiar with if you're familiar with the E department here. He works at the University of Honorice, which is a university in Nantes, France. We all studied in France last semester and got to work closely with him there. The University of Honorice is a food science and engineering school. So just like all good French food scientists that you know, they are in pursuit of cooking the most perfect baguette. Obviously, we electrical engineers then are tasked to help them. So they've tasked Grove City to produce a product similar to one that's seen on the screen here, which is a sensor array microcontroller. This has three main parts. It's got a circuit payload, which is here in the center, the silver part. It's a thermal barrier, which closes like a clamshell around that circuit payload, and then sensors, which are detachable on either end. These sensors gather information for temperature, heat flux, and humidity. And you can see on the bottom right of the screen a couple of the on-market today products that gather this information and the cost of them. So they've tasked Grove City with producing a similar product at a lower price point so that they can gather that information at their college and then produce the most perfect baguette for France and make all the money in the French world. So this is the third year. It's the third year of a 5-year project, or 5 to however long it's going to take us to make it. For this project, and the first 2 years produced printed circuit boards, thermal barrier prototypes. They did a lot of work with Arduinos and microcontrollers, and we were able to use some of their work that they created in the past to start folding our work for this year. But our project goals were to optimize software, optimize the circuit payload, and optimize temperature sensing accuracy within this product as it goes on to future years of this project. So to talk more about how we started doing this, we're going to have Joseph Tafaka.
Thank you, Matt. So with us being kind of a unique case, with spending a semester in France and a semester in the United States, we realized our development platform was very important for us. So we ended up looking at 3 main platforms: LabVIEW, which would utilize a MyRio microcontroller; Mbed, ARM Mbed, which would utilize ARM chips; and Arduino. We liked LabVIEW because it was really powerful, but we started to realize it was less viable in France because it's a lot harder to get there, and because of copyright laws, it would be a lot more difficult to use. We liked ARM as well, but we didn't have too much familiarity with it, and it was also a little more expensive than Arduino. Arduino was the least expensive, which was what we ended up choosing, and it had extensive documentation for us to use, and it really allowed us to use it in France more because it's produced in Italy. Next slide, please. Here you can see some of the Arduino ecosystem that we use. On the far left is the Nano, which is low cost and a minimal height requirement with minimal power consumption. Arduino Uno, which is kind of like the building blocks for all Arduinos. If you know how to use an Arduino Uno, you know how to use a Nano and a Mega, which is why we started with that. And the Arduino Mega, which is a bigger width than the other Arduinos, but it has a lot more sensor ports for us to utilize. And we also did some work with the Arduino Dewey, which has some of the benefits of the Mega while also being much more powerful. And what we liked about ARM was also utilized in the Dewey because it utilizes ARM microchip. And we had 2 main parts. There's 2 main parts of the project: the thermal barrier, which will cover the actual sensor array itself, and the circuit payload, which is where we worked. Here you can see the 4 different Arduino units we use and what goals they accomplished for us. And up next, to talk more about the Dewey and the Mega, is Andrew Hanby.
All right, thank you, Joey. So as you can see, the Arduino Mega was our prototype to display viability. That's where the bulk of our work happened. This is a picture of the prototype right here. So right there, you're seeing the microcontroller. That's the Arduino Mega. That's what you're buying when you buy an Arduino Mega. Then we have 8 thermocouple amplifiers, which you'd normally see 8 thermocouples attached, but to clean up the picture, you don't see those there. Those are digital thermocouple amplifiers, and I'll be talking more about thermocouple amplifiers later because we had a lot of different options in that area. We have a micro SD card reader, which is how we stored our data. So to access the data, you just pop out the micro SD card, put it in your computer, and you can access the data in text files. Then we have a chronodot. The chronodot was an addition this semester. It is a real-time clock which allows us to timestamp our data. That's just a really helpful feature if you're taking data from a lot of ovens or a lot of data for other applications. You want to be able to see what set of data you're looking at rather than just seeing a file named data1 or data2. You can look and see this was at this time. We also have a push button for starting and stopping tests and 2 LEDs which indicate our sampling rate and when we're writing and reading from the SD card. Now to get right down to our prototype actually working. So right here you can see a video of the Mega prototype in action. The Mega was our flagship prototype last semester during our work in France. So you can see the light flashing on and off as the data is being plotted. Our sample rate is once per second. And we had a time duration of 30 seconds. You can see that at this point, we did not have the chronodot, so our time is in seconds rather than a timestamp. And also of note, so those are the thermocouples. You can see that wiry mess. So there, we're taking that data in air, which is of note because when taking data with certain thermocouple amplifiers in water, you can create grounding loops, which we found out and created some issues in benchmarking those amplifiers and assessing the accuracy of our temperature sensors. And that's something which will still have to be ironed out more in the future. So our other prototype, and what was intended to be our flagship prototype this semester, was based on the Arduino DUI, which is really supposed to be the same as the Mega, but running a different microcontroller. And also, the other main difference is that we're running a different type of thermocouple amplifiers, and those type of thermocouple amplifiers allow us to use K-type thermocouples, which basically are more accurate than T-type. And I'll be talking more about the thermocouples in just a minute. But, right, so again, we have the DUI microcontroller. It's ARM-based, and we have the same components, 8 thermocouple amplifiers, a chronodot, and a push button and LEDs. So everything there is the same. The main difference is that we're running a different microcontroller. Now we hoped that that would mean that we'd be able to get the exact same results and everything working the same way on this prototype as on the Mega. However, as things go, that was not the case exactly. Right here, you can see some of our data. So the first thing that's helpful to notice is that the data on this, as far as accuracy goes, looks really good. That's mostly due to the use of the K-type thermocouples. Those K-type thermocouples have an accuracy of plus or minus 1 degree Celsius, where our prototype from last semester was plus or minus 2 degrees Celsius. So that may not sound like a huge difference, but talking to our sponsor in France, Dr. Hervé, he was very interested in the accuracy we'd be able to produce. So working with these K-type thermocouples on this prototype is a step towards that accuracy which we need to have in order to be a viable prototype. And that goes back to the idea that the DUI is supposed to promote the commercialization, the commercial viability of a product. The DUI is a more reliable microcontroller and really a more professional result. Now, we have not had complete success. Down there you can see the timestamps, but our sampling rate here was, instead of once per second, we had it about 2.5 times per second. Or sorry, one sample every 2.5 seconds. So that was mainly due to the protocol this was using and some issues with the libraries, which would take a little bit more work in the software to iron that out. Now I'd like to talk some more about the amplifiers in particular, discussing the accuracies and the different options we had. In the past, groups worked with both analog and digital amplifiers. So we compared the two that they had used most often. That would be the AD8495 and the Max through an 855. So this first plot you see is it's our benchmark data. That is from a vernier thermistor. Those are highly accurate but have slow response times. So we used boiling water bath and ice water bath to benchmark these amplifiers. That's our digital data. You can see that it's pretty close. These are the T-type thermocouples, and so we should be expecting plus or minus 2.2 degrees Celsius, and we're getting much better than that, which practically is common. And then we have our analog data, which does not look quite as good. We were kind of anticipating that the analog data would be more susceptible to noise, and it looks like that's definitely true. However, we'd like to work more in exploring the ground loop issues to make sure that the noise isn't as easy as eliminating that ground loop. We also worked with T-type thermocouples, as I said. Those thermocouples only work with a specific type of amplifier. Those amplifiers are a little bit more expensive, but they allow us to use these thermocouples, which are much more accurate. So we did the same calibration test, and we got very good results. You can see our standard deviation on those right there. This is well below the accuracies that are reported on the data sheets. And we were really happy to see that. Honoris actually has some calibration equipment which is much better than using an ice bath and these calibration techniques, and we'd like to see the continued use of these T-type thermocouples, but confirming their accuracy using that more reliable calibration equipment. So to summarize, we tried a lot of amplifiers. The top two are the ones that we've worked with the most over our project this year. The top one is the universal thermocouple amplifier, which is compatible with the more accurate T-type thermocouples. And that's what we'd like to see transitions to in the future. It's compatible with both the Mega and the DUI, so any concerns with working with the DUI aren't really an issue, just to use this other type of thermocouple. But we still have used a lot of Max through an 855 K-type amplifiers, and because we have so many of them in France and that's what our prototypes are right now, we expect that they'll probably be used in some testing capacity for testing things like the thermal barrier. Now to move on, I'm sure you've heard enough about temperature sensors, but there are also two other types of sensors which we'd like to see for this project: humidity sensors and heat flux sensors. And talking about the viability of specifically humidity sensors, we did some proof of concept work, which Melody's going to talk about.
Good evening. So we wanted to look forward, as Andrew said, into developing humidity sensors into our prototypes. And so we created a bang-bang control system prototype on the Arduino Uno, you can see the fritzing diagram and the block diagram, but videos are more interesting. So on the next slide, you're going to see a video of our Bang Bang control system. The Bang Bang control system just turns something off and on so it oscillates within the range that you want it to oscillate. And so the lone red light can tell you when our resistor is powered on and when it's powered off through a relay. And the thermocouple that is sensing it tells us whether it's getting cold, whether it's in the middle in our optimal array, at which point it's yellow, or whether it's getting too hot, at which point it's red, and cold is green. And you can see it fluctuating through those states and trying to stay within the yellow zone so that it is within a certain heat range. And on the graph, you can see it going between 32 degrees Celsius and 40 degrees Celsius. And the reason this is important to our future with humidity sensors is we need to create a control system that can take in temperature data and go ahead and respond to that and figure out what it needs to do with the sensor, because the humidity sensor needs to take a sample of air in, cool it down, measure the humidity in that air sample, and then take another sample of air in. So this is the beginning of the future of our project. And now Dalton Mesmer is going to talk to you about the software for the Mega and the Dewey.
So as Melody said, I will be talking about the Arduino software. So shown here is an activity diagram for our Arduino Mega prototype. The top row represents the setup portion of the code, which runs once when the Arduino is first powered on. So it's in this row that it initializes the thermocouples, the SD card, and the real-time clock. And it also reads a config file to know the test configurations. So everything below the top row represents the main loop of the code. It's in this loop that it checks the data on the thermocouples, and it writes the data to the SD card, and it does communication with a PC that's connected to the Arduino. So the process of changing test configurations can be confusing and time-consuming for many users. So to solve this problem, we created a Windows application to make the whole process a lot easier. So here on the left is a screenshot of our Windows application. It's made in C#, and it runs on Windows 10 and Windows 8.1. One feature is that it can automatically connect to any sensor array that's connected to the computer, and any Arduino Mega based sensor array. And as you can see on the top right of the screenshot, there's an option to choose languages. So there's currently English and French, and it's coded in a way to make it easy to add more languages as well. And so there's also an installer that's included with the source code, which makes the installation of the sensor array software very easy. So as you can see on the top left, there's 4 main tabs in the application: status, config, sensors, and data tabs. Currently it's on the config page, which is the most important tab in the software because it allows the user to edit the configurations that they use in the test. And once the configurations are edited in the UI here, the user can simply click the sync button at the bottom, and it will sync all the changes with the Arduino. So in order to sync with the Arduino, it has to overwrite the config.txt file, which you can see on the bottom right there. That's a screenshot of the contents of the SD card. So without this Windows application, the user would have to do this manually. And this application also provides a way for synchronizing the time and date for the timestamps as well, as you can see there. Without this program, that would be an extremely difficult task. So it makes it a lot easier. So currently, the sensors and data tabs are not implemented, but in the future, we would like to implement those. And as I said before, this communicates with our Arduino Mega prototypes. Doesn't currently work for our DOI prototype, so in the future, another thing we would like to do is, or a future group should do, is to port the code over to the DOI so that the DOI can also work with this program. So now looking at the Windows applications code, you can see that it's divided up into a few major classes. At the top is the main class, which is the graphical user interface, or GUI, of the program. That's the part that the user will interact with. And the main object has a serial interface object. And the serial interface object is what manages the Arduino, or a collection of Arduinos that are connected to the computer. Because this application supports having more than one sensor array connected to the computer at one time. And it needs to be able to manage all of those that are connected. And the serial interface object is also used for automatically connecting to sensor arrays that are, when they are plugged in to the computer, and disconnecting from them when they are physically disconnected from the computer. So the serial interface object has Arduino board objects, which are like software representations of the Arduinos. And they allow an easy and also extendable way of communicating with the Arduinos. So to conclude, the Windows application provides a quick and easy to use interface for interacting with the Arduinos. Up next is Ben, who will be talking about our budget.
As Dalton said, I'm Ben. So one of the interesting things about our group as opposed to the other groups is that we couldn't bring anything back that we made from France to the US, so anything we made there, we had to re-replicate. So the things that we had to do were, obviously we wanted to replicate everything that we made in France, as well as keep developing the project here. So once we got back to the States, one of the first things we did was take an inventory of the lab, and then compare it with the parts that we needed, and we came up with the parts that we were going to buy, and that's all on the list here. The total came out to around $820 out of a total budget of $1,500, so we did pretty good on that front. After this, we sorted the inventory into 5 categories so that we could sort it into a percentage for each type into the budget. You can see there that most of the project went into these 3 left categories of thermocouple amps, Arduinos, and just thermocouples themselves. On the next slide after this, you can see our Pareto diagram. So Pareto's theory says that usually that 80% of objects are going to end up in about 20% of the grouping. When you apply that to something like an engineering project budget, that means that about 20% of the objects are going to accumulate for 20% of the price. That's true here because these first 2 categories, the thermocouple amps and Arduinos, which is about 20% of our objects, kind of accumulated for 79% of the price. And the first 3 categories are 90% of our price, which matches Pareto's theory pretty well. Pareto's theory might sound kind of useless, but it's really actually pretty useful. because by examining what our 20% and 80% were, we can tell where our priorities were, and hopefully future teams won't have to spend as much time on them, and we can sort of streamline those things for the future. Next, Matt will tell sort of a conclusion and about the future.
Thanks, Ben.
So this school year we were able to optimize our software by creating a user-friendly interface that people would be easy to install when they're running our Mega prototype. And we also showed with both our Mega and Dewey prototypes that we can timestamp our data, which is a standard in the industry today. As far as our thermocouples and amplifiers, we showed that digital amplifiers were more accurate than analog amplifiers, and that T was a better thermocouple to use than the K-type thermocouples. So in conclusion, we had two primary prototypes. The Mega prototype and the Dewey prototype. Our Mega prototype, which is both here and in France, is going to be ideal for next year's group because it does have a user interface associated with it. It's easy to run. It's got 8 functional thermocouples attached to it, and you can press a button on it and just have it start collecting data immediately. Next year's group is going to focus on creating a functional thermal barrier around it and actually try to do some high temperature testing. So since there's a functional 8 thermocouple sensor they can put in an oven and actually collect data, it'll be great for them to hit the ground running with. The Dewey is kind of the prototype of the future. It doesn't have the user interface that the Mega does. The Dewey doesn't have the same community online with code assistance that our other Arduino products do because it's a newer product and it has the ARM chip. But because of its ARM chip, it is much faster, much more intelligent, and it has a lot higher ceiling for when we actually do end up implementing our future sensors in these prototypes. Once again, I'd like to thank you all for coming out here this evening, and I would like to open the floor up to any questions.
What is the difference between the K and T types?
Great. So I think I might have misspoke, got my letters mixed up. So the K-type thermocouples are the ones which, so they're made of different metals. The K-types are less accurate than the T-types. So the T-types are what we've been using this semester, but they can only be used on certain amplifiers because basically the thermocouple outputs a small voltage signal which has to be scaled, and so you have to have a different amp to scale it appropriately, and they also output different signal levels.
I had a question in terms of accuracy going forward. The T versus K, would it mean that we probably would be leaning towards the T in terms of accuracy? And in terms of the accuracy, is the Dewey clearly, does it give better, more accurate results, temperature results, or are there other advantages?
So I think we can't, our tests haven't been sophisticated enough of just doing like ice baths to say, evaluate the microcontroller specifically. But the advantages of the Dewey, I think, are clear in terms of its hardware reliability, and there's a certain expectancies attached to the ARM name, and also it's more powerful. So when you're talking running 8 sensors minimum on a Mega, then you're starting to think, I wonder how much this thing can handle. But for the Dewey, that's not a concern, and that's why we like the Dewey for the future.
Sure. Any other questions?
Are all those amplifiers externally powered, or is it coming straight through the Arduino chip?
Yeah, they're straight from the Arduino.
Okay, well done, thank you.